Now I would like to invite Mr. Naveen Rajan, lead architect at Wipro, to share his thoughts on scaling ML workloads with the Ray framework. He has 25 years experience across object-oriented client-server, web, relational, non-relational, cloud, NLP, and AI technologies across product development and consulting engagements. I welcome you, sir.
Hello, Priyanka. I would like to share my screen.
Yes, yes, sir. Okay, now it is
Yeah.
visible.
Hello, everybody. So, I'm Naveen. I work for Wipro. Today, I'd like to talk to you about a very interesting challenge that we have both in the industry and also, I guess, would something that you would be interested about because you are looking at a lot of data from that will be gathering from various sources like UAV, drones, satellite, and stuff like that. So to begin with, so why another framework? That would be the first question on many people's minds. And actually, the Ray framework is from the same university team that built the Apache Spark. That was about more than a decade ago, and that was a very successful framework. But that was in another era where there was not much of AI. Apps are increasingly incorporating AI across every industry. So AI is everywhere. And if you look at the AI computational requirements for AI, if you look at the some popular models that have been published for the last decade, the computational requirements are increasing almost 35x every 18 months. But if you see the Moore's law, it cannot keep up at that rate. Though we have other innovations like TPU and GPU, they also cannot keep up with the demand. That means we have enormous amounts of data and we want models with high accuracy. That means we need more computation to give us more accurate models. And what is happening is that means you cannot do some that computation in one machine or even a few machines. That means it's distributed by nature. That means AI demands distributed computing. Apps are becoming more complex. Going from development to production is challenging. In fact, this figure down below shows that there are many tools which are very good when you're doing development on a laptop with 1 KB of data. But when you want to do deployment and process, say, 1 TB plus of data, the same tools don't work anymore. You have to change your whole tool set. That's very expensive. And how is the industry getting by right now? So basically, we are stitching together different solutions. So when you look at a different processing pillars like data processing, ML training, serving is model inference, hyperparameter tuning. Hyperparameter tuning is another side effect. I'm not sure if you folks know, when you build a model, the model's accuracy can be tuned with a lot of increase in percentage points just by tuning a few hyperparameters. That is known as hyperparameter tuning. And then finally, it has to talk to the business logic as well. That's from the deployment perspective. But stitching together so many different solutions is hard to develop because it has different APIs, hard to deploy and manage. There's an impedance mismatch, slow because there is high overhead of moving data between different systems. And this is a sample stitched architecture showing online learning. Online learning is something wherein your choice, say for example, your choice of a particular YouTube video will affect the results that you will see next time or instantly in after 2 minutes. That means there is a feedback loop between what the customer chose and what you are going to see after, say, 5 minutes. So just for these stages of data ingestion and featureization, training and serving, we have a bunch of products that we use. There's Apache, Spark or Flink, Kafka, Dask, and then for training is either the family of TensorFlow or PyTorch. And then you see there down below there is this sibling Hyperparameter Tuning. In fact, there you have two products. And when it comes to serving the model, then you have two more products there. I've just shown two there. One is TensorFlow Serving and Seldon. And in fact, we had used some more open source product like BERT as a service and stuff like that. So I'm just showing you the problems that we are facing right now. This is same in reinforcement learning. Reinforcement learning, you might have heard, it's like, like how computers learn to play video games, or the game of Go. That means here there is no labeled data and annotation and all that. It just plays, makes a mistake. It knows that it made a mistake. And then it does another move again, which is all by pure chance. Then it knows that this time it got it right. The same technique, computer robot can use to grip a cup. It will know how to grip a cup. So for a lot of these architectures, we are using these stitching together a lot of products together, and same with deploying. For example, Flask was originally for deploying web applications, but we now even deploy our ML models onto Flask. So now I'll just take into the how. I'll take a look into the how. How does Ray framework solve some of those problems? So if you see the two blocks in that color are called tasks and actors. Actually, this is the core of anything, and functions and classes are actually the core of any programming language. If you can enable some kind of remote procedure calls on your functions and classes, you have really solved the problem of distributed computing. So everything else is built on top of this layer, if you notice. So we will take a look at tasks. What are tasks? Tasks are just any other function written in Python. But what makes it special is that simple annotation that you've added on top of your function called @Ray remote. You just mentioned that and basically you now have two functions that can be remotely executed either on your laptop, on your multiple cores on your laptop, or on a cluster. And also, if you notice how we are invoking that function called zeros, we are also appending a .remote suffix there. And also, if you notice, this method actually returns immediately. And if you notice the method called dot, it also takes two parameters, but they don't have to be actual. They can be your what you call futures, because the way it works is it will immediately return you a future. Future is something like a token that you can use at a later point to get your data. So when you call ray.get, that is when it is doing the actual execution. Until then, it's more like a lazy evaluation. So, and for example, I'm showing another function here. It is the function f. All it is doing is return true, but the ray annotation, we have also told it one more thing. We have told it that this function requires two CPUs, and that is that it can use that for resource aware scheduling. For example, I have a loop down below there which calls the same function 3 times in a loop. In a prior generation of software, that would have been executed one by one, 3 times, one after the other, serially. But with Ray, you can actually do that in parallel, assuming you have 6 CPUs. That will just be fanned out to 2 CPUs each, and they will so what you achieved is fine-grained load balancing. You can think of it as multi-processing on steroids, multi-processing across a cluster, and at the same time it comes with efficient failure handling. And so that means essentially we have achieved distributed computing for a function. Now we look at the next building block, that is naturally a class. A class is actually used to encapsulate state. State means, say, can be like how much bank balance you have or anything like that, a model. So that is a state, right? So state also can be remotely accessed, and so that we achieve again in a very simple API by slapping remote annotation onto an existing class. And also we are also specifying that this code requires one GPU. And if you notice, even while creating the class or invoking a method on the class, we are still using the remote annotation. And finally, when we call ray.get, you get your answer. So basically it achieved helped us achieve coarse-grained stateful load balancing with classes and low overhead for small updates. So when you call ray.increment, I mean c.increment in the above class, there is really no overhead. So now we'll put all these together and see how it solves the problems that we face. For example, we take one problem called data parallelism. Say when you want to train a model, typically you have a lot of data. Say in the couple of lectures ago, I saw you had a lot of data about Northeast and Assam, and inside Assam you had data about multiple districts. So you can think of data parallelism as some kind of divide and conquer. So basically you're sending off one batch of data to one GPU. So these GPUs are working in parallel, and while they are working in parallel, they also need to update the weights. The weights are the unified. You have one set of weights for your model, but these GPUs are computing weights and updating the weights, right? So they need to send it off to a central unit, which is known as a parameter server. The parameter server can then do things like average once it gets the results from a worker GPU1, it will take that and average it. And then the next time another worker asks for the data, it will send it off to that worker. So this is the way the different workers, though they are doing parallel processing, they're also using the parameter server to synchronize their work. So for example, in this code block, and also I have got a link here in the footer. So it shows you how simple in 15 lines of code you can achieve this parameter server in a distributed environment. So there's on the left hand side code block, you see the parameter server. It is a class annotated with the remote, and all it is doing, it has two functions there, get params and update params. On the right hand side, you have the worker processes. The worker processes are working on a farm of GPUs. As you notice that the worker has a reference to the parameter server. That is because the worker will initially, before starting the work, he'll get the parameters, and then he'll do the training on his batch of data. That batch of data could be either a district in Assam or a state in the Northeast. So then once you do that number crunching, you send the update back to the parameter server. The parameter server will average that data. So your model is synchronized across your various worker nodes. So the same paradigm actually has been used in ray-SGD. ray-SGD is a library built on top of Ray for distributed training. So, and I'll just to take a detour now, I will hyperparameter tuning. I also mentioned so a few minutes back that hyperparameter tuning is also a very important part of your model building, wherein you tune parameters related to your model, which will actually greatly help in increasing the accuracy of your model. So in fact, there's a trivia question here. What's the connection between a 3,000-year-old Egyptian pharaoh's tomb and ML training? Actually, the answer is grid search. If you notice, grid search is actually one of the approaches in that is used in hyperparameter tuning. So, for example, about 100 years ago, the desert in Egypt was divided into grids and searched for 4 years to find the tomb. And in fact, they found all these gold treasures in the tomb only after searching for 4 years. In a sense, the machine learning scientists' work is also a little something similar, because they are searching for the hyperparameters, which is both expensive and time consuming. So now I will just quickly walk you through another library which is also built on top of Ray, which is called Tune. So this is distributed hyperparameter search. So this with and it since it is being built newly, it is built with the focus or priority for deep learning. And as you know, resource aware scheduling comes by default with Ray, because if you remember the annotations, we also mentioned how many GPUs or CPUs are required for each class and for each function. And Ray, by its very nature, is distributed. And another requirement for hyperparameter tuning is it should be framework agnostic. What I mean by that is, in the past we had these families, of frameworks. One is only TensorFlow family, another is a PyTorch family. So the tuning should work across these families of algorithms that you built your code on, and also it should be future proof. It should support new algorithms. And last but not the least, it should help in reducing cost. Like as I said, hyperparameter search is very expensive in both computation and time. So any feature that will help in reducing cost we should focus on that. So early termination. So suppose there's some hyperparameter that is not really promising, then you can terminate that trial immediately. So that will help in reducing the cost as well. So, and another deep dive here into the Ray Tune, you see that as everything else in Ray, it supports either you can do it the function way or the class way. And also from a search algorithm perspective, you can either use a grid search or you can use Bayesian optimization. And also they have introduced something called trial schedulers. These trial schedulers are the ones who actually monitor a trial, and if a trial is not promising, the trial will be terminated, thereby saving you a lot of money in your model building and hyperparameter search phases. Well, that means you're not unnecessarily using compute resources. And the third library I would like to focus on with Ray, that is built on top of Ray, is RayServe. RayServe, as the name says, is used for serving a model. So you might previously, about 10 years back, when you had gone to a bank, you just have the web application in the bank. But now if you apply for a loan in the bank, that loan application might get rejected or approved by a model. So that means there is something else there other than just your web application. So that is the model serving. So model serving, what are the requirements for model serving? One, of course, is the most simple one, or most basic one, is deliver the prediction. So whether it's a bank application or image classification or whatever, it's a basic 101, deliver predictions. The second one, it should support, again, it should work across frameworks. So suppose some part of your model is in TensorFlow, another is in PyTorch, the third model is in XGBoost. Your serving should be agnostic of the framework that you use to build the model. The third one could be like pre-processing and post-processing. In fact, just in the previous lecture, there was an interesting lecture about decomposing, scattering, and how that could be some of your pre-processing logic. Like before you uptake the image, you do some pre-processing. Only then after that it is supplied to the model to do the actual inference. And after processing also, you might want to do some post processing, like for example, you might want to know whether you want to understand the model, you want explainability or something like that. That is post processing, right? And then scaling. So there should be some kind of way for you to scale your model as your user load increases. And then batching means basically you're taking all those images, say in some district in Assam, and batching it so that you want to scale it. The batching is on a natural extension of it. And in fact, Array also supports another interesting side effect of batching. That means if you're dealing with a lot of images, and if you're spending time reading one image from your disk, at that point of time, the GPU might not sit idle. It can do another processing of another image as well. So it supports batching in multiple ways. And then, of course, high concurrency and low latency are also non-functional requirements. So, and if you look at how traditionally we have been addressing this requirement of model serving. So one of the first row there shows that we typically embed the model evaluation in a traditional web server. That means the same web server that 5 years ago was serving your web application. Now it is also, you put your model. So just like if I was looking at the bank had a website in the past. On the same web server, now you have added your model to, now that model will start evaluating your loan applications as well. But we'll look at the pros and cons of that. So if you embed a model right into your web server, this is how it might look. Say all the requests are coming into your Flask server, and one of them which says image predict or bank loan approval or something, that will go to the TensorFlow model. But what are the pros and cons of such an approach? The pros are, it's very simple. That means you, as a developer, you can continue doing what you did, say 5 years ago, wherein you deployed your web application. Same way you deploy a model also into the same endpoint. And it is very simple, but web serving and model serving are entirely different. So it's not neither supports concurrency nor scalability. We'll dig a little deeper into that. What I mean by web serving is not model serving, because typically on the left hand side you see a code snippet that's talking to a database, and on the right hand side is the same code which is doing inference in a model. But they're entirely different. When you're talking to a network, say a database, it's only network bound. But when you're using this model, it is compute and memory intensive. So what it means from a queries per second for the process. For example, a website can handle 10,000 queries per second. But same, depending on the complexity of the model, you can maybe handle only 10 or 100 queries per second. So, and you can even make that web service more efficient by having a pool of connections to a database. And then another point, when I mentioned that web serving is not model serving, because you can put your bank application on, say, 3 servers, and when you log in into your bank, your request goes to one of the servers. But when you're doing something like image processing, you might have different model. You might have a model for, say, soil health, or maybe one model, and maybe landslide prediction might be another model. So you might have to route your request to the appropriate model as well. So that means web serving is not model serving. So when it comes to the scorecard, it is a quick and dirty way to deploy your model. When you deploy your model to a Flask web server, just like we deployed code 5 years ago, but it is not good in terms of scaling or batching or high concurrency. So what is the other approach? The other approach would be you continue with your web server, but only when it comes to actual invocation of your model, you offload that to an external service provider running on either Google Cloud, Amazon Cloud, or something like that. So this on paper, it does look good. That means even like, for example, initially when you had a web service, it was only network bound because you were only talking to a database. It is still network bound. You're only talking to Google or Amazon, and the queries per second is still depending on how if you scale it up, you can still get your queries per second as well, can be handled. But there are some other subtle changes, one of which is, if you see separation of concern, it's really good. Concurrency and scalability, you get out of the box because you're actually outsourcing that to the cloud provider. But there is one side effect: added complexity. We'll take a look at that in this slide. Why do we say there is added complexity? Because, say, when you in the past, when you did all your inference, like even like in the previous talk, there was a mention of some pre-processing, like decomposition, scattering, how some pre-processing you're doing to your image, that previously when you had both deployed your inference as well as your input transformation, you had deployed it together in your Flask application. But what has happened now is that your input transformation and your output transformation are still inside your Flask web application tier, but only one piece of your code has moved to the cloud, the inference component. So that means there is added complexity in the sense that if you deploy a new version of your model onto the cloud, but there is, for some error, you did not update your transformation layer, you will have a flawed deployment. So when it comes to the scorecard, though it looks, by and large, it does look good, integration with business logic is not passing when it comes to when you offload your inference to an external service provider. So I'll have a quick look at 𝐸_serve. 𝐸_serve is the third library, by the way, which we are looking at, which is built on the 𝐸 framework. It is a framework built from scratch. It is a web framework built for ML serving. That means you can have arbitrary Python class or function, can serve the request. And apart from that, we have new concept called a backend, which encapsulates versioned model and configuration. And additionally, configuration can have a hardware specs. So you can say there should be this model should be deployed on 4 or 400 nodes or anything like that. And even when it comes to batch processing, you can say when you invoke this batch, it should have 32 images or something like that. So, and what it does is it takes you from an user experience perspective, closer to the Kubernetes experience. Kubernetes is how we deploy microservices, So basically, when you deploy microservices, you get a lot of, something like A/B testing. Say, suppose you built a new version of your model, you deploy it, but are you going to allow, maybe you did something a little risky when you deployed your new model, and you want to know whether it's performing well. You can do A/B testing. You can route only 20% of your users to your new model, 80% still to the old model. You can also do something known as canary testing. Canary testing means see whether it's working fine. Only after that you roll it out. So, and also you can also have model composition and deployment patterns. For example, you might have a chain of models. For example, after you execute one model, you might want to invoke another model for model explainability, or you might have an ensemble of models, say, wherein each model votes on some like a vote, and then you take the majority of those votes will what your model will vote for, like a democracy. So this kind of a very complex, or this is what you would need when your product putting your code in production. This is the kind of features that you would actually require. And coming to as a racer, see you see that all the right hand side there is check against almost every aspect of non-functional and functional aspects get a green tick. And now for a quick summary. So the big picture is use the same code for whether you're doing your POC on a laptop or you want to go to the production deployment. You can go stick to your same code. And also one more thing it brings about is standardization, because you're not changing multiple tools for every single pillar. There is a certain standardization, and that will itself drive productivity. And one more thing I would like you to notice, if you notice I had covered the items in the box on the left hand corner. Those are the libraries that were built by Ray themselves, by the Ray framework people, the Ray Tune, Ray SGD, Ray Serve, and those. But if you see on the right hand side, the third parties, there's a lot of adoption in the third parties. That means the third party tools which actually were kept out of the game because of the picture at the bottom. If you see the picture at the bottom, I've showed the tools good at 1 KB are not good at 1 TB plus of data. So a lot of tools like Pandas, Spacey were not able to enter this space. But now, for example, Modin actually allows you to use and these are all plugin replacements. Plugin replacement means you don't have to change your code. You have to just change your import statement. Previously, if you had imported pandas, now you just say modin.pandas. That means your code will now be able to deal with 1 terabyte plus of data. That's because the distributed nature of work, all the other things are taken care under the hood by the universal framework for distributed computing, which is Ray. And as a case study, I would just like to mention this Dendra Systems, which is actually focuses on scalable ecological restoration and monitoring. I've also included a link to the blog. And in fact, this I believe would be very interesting to you folks, because you have a similar view of the world, because they also look at things like biodiversity assessments, weed management, pest management, erosion, and soil health monitoring and stuff like that. So in fact, they use Ray framework for things like ML training, tuning, as well as model inference. And so this is a very good use case for case study for a similar use case. So I included that. And in fact, I can, I've included the link here, but you can also, this is the link, I'm sure the audience here would be very much interested in this blog post. You can go check this blog post when you are free. This is about how they are using for a lot of the problems that you are, say, for example, these are images that are gathered by drones, and they gather these from this footage, they build machine learning models, and then they draw inference from these models and all of this. So I'm sure and this audience here would love this case study. And last but not the least, I would like to thank Dr. Alok Mukherjee for this opportunity, and also like to thank Leads Connect and BIT for all your work in helping India fight climate change, as well as help and raise and sustain farm incomes for our farmers. So thank you.